label the children of the root from left to right by 0, 1, blah, blah. Okay? So this is going to be labeled 0. This is 1. This is 2. This is 3. And this is going to be 4. You with me? Okay? And then the numbers, blah, blah, no, they are not distinct, as you can see. So therefore, we may have bouquets that might be dangling from the same node. So the next step we're going to do is, I probably skipped something here. See, and hang bouquets of size B1 minus A2, B2 minus A3, blah, blah, to each of these vertices that I labeled 0 through 4. Okay? So the sizes are, you're going to take differences this way. Don't worry about this. You're going to go this way, this way, this way, this way, this way, and that way. Let's write the numbers now. So you're going to be doing 2 minus 0, which is 2. 3 minus 0, 3. 6 minus 1, 5. 7 minus, what did I do next? 7 minus 3 is 4. 4 minus 3, 1. 6 minus 3, okay, 3. And then 6 minus 4, 2. Okay? So we're going to be hanging bouquets of size 2, 3, 5, 4, 1, 3, and 2 to each of, okay, the vertices that I have over there. What is the rule? The rule is you're going to be hanging bouquet of size 2, okay, to a vertex level 0, bouquet of size 3 to a vertex level 0, bouquet of size 5 to 1, and so on. You with me on that? Okay. So if you do that, then the first one, you're going to give me the bouquet size from there. The first one is 2, right? So it's going to be just that. The next one is still 0, right? What size is it?
3.
3. So it's going to be like this and like that. What the next one?
5.
It's going to be hanging from where?
1.
1. Okay. 1, and then 1, 2, 3, and 4. Next one? What size?
It's hanging from 3.
Okay. What size?
4.
4. Okay. 1. That's size 4. What's the next one?
1. Size 1 hanging from
3, right?
Yeah.
Good. How about the next one?
Size 3 hanging from 3.
Okay, good. Size 3, right?
Yeah.
How about the last one?
Size 2
Hanging from 4, right? Like that. And you're done. So that is the tree of height at most 3, okay? That corresponds to this directed column convex polyomino. Really, to complete this proof, what they have to do is show that the order tree that we have constructed has n edges. Okay? Yeah.
Do you already have the function? I forgot. Did you give the function?
I'm going to get there.
Not yet.
Yeah. I intentionally wanted to do this one first.
Yeah.
Okay? So,
Very nice.
yeah. So, if you show that the tree that you construct this way has n edges, pretty much going back is quite trivial, and therefore finding out that the tree has n edges is just adding up, you know, the number of edges dangling from each one of them. The first one obviously is BW. If you rearrange terms, you will see that it's going to be just this sum, and each one of these things are the number of cells in every column, and then you end up getting n very easily from that. Okay?
So it has to be exactly 3, level 3.
Huh?
It has to be a level exactly depth 3.
Not necessarily. Not necessarily. Yeah, so these guys could all be 0, and then you might end.
Oh yeah, so
yeah.
empty.
Yeah, okay. So at most 3 is the correct description, okay? All right, so the inverse mapping, going from trees of height at most 3 backwards, instead of taking the difference, if you add them up, you can very easily get it. So it's quite easy. I'm not going to go through the details. You think about it. Going back from the tree to this guy's is quite easy. Instead of taking the difference, you add them up and so on. Okay? So this is one of the 2 bijections they gave in their paper. I thought that this one is more complicated, so I wanted to confuse you. So that's why I presented the more complicated one. Now I get to your question. I intentionally wanted to do the iterative function later. So let's try to enumerate either the directed column convex polyominoes or the number of order trees that end at height at most 3. But this one is quite easy to enumerate in terms of generating functions. You look at the structure here. Any directed column convex polyomino, if you assume that it is non-empty, is going to be either like this, where the bottom row has exactly one cell, or the bottom row is going to have more than one cell. Okay? So now if you put this into a functional equation, you end up getting that. The generating function will have this particular form, where here I used 1 to denote the case of empty, okay? Directed column convex polyomino, and you do the trivial algebra there, and you end up getting that Cp of z minus 1. This is the number, the generating function for the number of non-empty directed column convex polyominoes is again the same as the previous rational function that we have noticed with contiguous fountain of coins, skinny trees, and so on, and therefore these guys are also enumerated by every other Fibonacci number. And now the conclusion is that the number of directed column convex polyominoes with n cells, which is equal to the number of n-edge order trees of height at most 3, is also enumerated by every other Fibonacci numbers. And in fact, in OEIS, they put in this particular sequence with all, its descriptions and so on and so on. Okay, it's not a new thing. Now, in our case, we wanted to connect the pieces. So we noticed that in terms of order trees, myself and Dr. Johnny, we study order trees and their generalizations. To us, the coins, the directed column convex polyominoes, and so on are just side issues. The skinny trees and the trees of height at most 3. Those are the kind of things we are interested in, and we wanted to provide a bijection between the skinny trees and order trees of height at most 3, because we know by now that both of them are enumerated by every other Fibonacci number. We have equal numbers of skinny trees on n edges and order trees of height at most 3 with n edges. So we wanted to provide a bijection between the two. And if you want to go directly from, for example, these Emeric trees to skinny trees, you start with an order tree of height at most 3 on n edges and convert it into a dict path. This is a very standard thing, up-down thing. Okay? You convert it into a dict path. Now, since each dict path is either a 0, 1, or an up step or a down step, so it's going to be represented by a UD word of length 2n. And we want you to scan that UD word from left to right and look for the first UU occurring after DD. Why are we asking for this? Let me just describe this quickly because it's quite important. This is the smallest size, non-empty, non-skinny tree that you can find. This is the smallest troublemaker. If you are going after skinny trees, you want to avoid this guy or its byproducts. So therefore, in terms of the UD word description of ordered trees, you want to locate these guys and get rid of them. So that can be done by looking for a subword of the form DD. It doesn't matter what you have in the middle, UU, okay? And here this represents a valley of depth 2. Valley of depth 2 in the dict path language means that troublemaker there, okay? Now when you see this, you interchange the DDs to UU and the UUs to DD. That way you're going to get rid of these guys, okay? So our step here is interchange U and D throughout the subword obtained in the previous step, and you repeat that until your UD word is free of these kinds of subwords. Free of these kinds of subword means your tree, the corresponding tree, will not have the troublemakers or its byproducts. So in the end, you will obviously get a skinny tree because we have eliminated all possibilities for two vertices to have the same level and so on. Okay? At the same level to have different patterns. You can go back in the same way. This time around, instead of scanning from left to right, you got to scan from right to left. We have to be careful here. The dict path condition has to be there when we scan from right to left. You have to always have more up steps, okay, than down steps up until you get back to the x-axis and so on. But with a little bit of care, it can be done. And here is just two examples quickly. This is an example of a non-skinny tree of height at most 3. Okay? And we want to map these to a skinny tree. Obviously, since this is non-skinny, you expect the level of these to be more than 3 and so on. Okay? So this one maps to this. You see, this is the first occurrence of DDU, DUU, and then you flip that, and then now you get this one. This one is DDUU free and so on. You take this example. Sometimes it takes more than one step, so that's why I showed you here. But these sequence of UD words in our algorithm are unique. And therefore, you can use that fact in order to provide a justification that this is indeed a bijection. So quickly to Shapiro's identity. In my last talk, I described reordered arrays, and reordered arrays are defined based on 2 generating functions. The first one here, you just take a generating function G and F, and if you take the column generating functions for your infinite lower triangular matrix to be of this form, pretty much what I'm saying here is you form an infinite lower triangular matrix of this form. You start, the first column has to be the entries of G. The next one is G times F. Okay. The next guy is G times F squared and so on. That, and you continue this process. If you get a matrix in this form, we call that a reordered array generated by F and G. Okay. I talked about these in my last presentation, and there is a statement known as the fundamental theorem of reordered array, which I also described last time. This one is, if you take A of Z and B of Z to be the generating functions for 2 column vectors A and B. These are 2 column vectors. And these guys are the generating functions. So we do have this relationship that the reordered array generated by G and F multiplied by the column vector A is equal to another column vector B if and only if their respective generating functions satisfy these kind of composition property. You with me on that? This is called the fundamental theorem of reordered arrays. And now, Lucia Field applied this particular thing to a reordered array D, where the G function is 1, and F is Z times C of Z squared. Here, C represents the Catalan generating function. Okay? And also, you probably know that the Catalan generating function satisfies this simple functional equation, and therefore C of Z minus 1 is equal to Z times C of Z squared. So this thing really is a generating function for non-empty ordered trees, or where you remove the first case from your Catalan sequence and so on. He looked at that, he looked at these reordered array, and he multiplied it. Don't ask me where he got these column vector from. Somehow, out of the blue, he got these column vector, he multiplied his reordered array by this column vector and got this sequence here. Do you recognize this? These are every other Fibonacci numbers, the one that we've been talking about before. Okay? It's a completely different approach. And now, of course, he applied the fundamental theorem of reordered arrays to what he observed, because the generating function for the column vector that he used is obviously this one. And he noticed that, well, it's a conjecture in his case, since what you see on the right-hand side is every other Fibonacci number, and we know that their generating function is this, he gets this identity. And he asked us if we can provide some kind of combinatorial proof. Now, since ZC squared, as I described over there, is a generating function for non-empty ordered trees, we kind of insisted on using ordered trees, and our attempt eventually paid off. And his identity is actually no big deal. All you have to do is take that formula, solve these for Z. If you solve these for Z, you get C of Z minus 1 over C of Z squared, and replace every occurrence of Z in the generating function for the R Fibonacci numbers, and you do the tedious algebra, and in the end, you end up getting his identity. He's not very happy about our proof, because he's asking for a rather straightforward combinatorial proof, not algebraic proof. Okay? As far as we are concerned, at least we gave him some answers. Now, look at these identity. There's something interesting about this. Other than the skinny tree business, these guys also count ordered trees of height at most 3, right? So when you have a generating function for ordered trees of height at most 3, and you have these kind of more Kaplan type thing with exponents 2, 4, and 5 here, you might be curious to ask, what if we consider ordered trees of height at most m? How will those powers change? And it was not difficult for us also to obtain. If you extend it to height at most m instead of height at most 3, the generating function will be of this form. Okay? So this is for height at most 3.
But then it's probably not rational anymore.
It's going to, okay, good question. We believe 99% that it's going to be a rational function. We are still working on it with the help of Mathematica.
So you can check it for small m.
Yeah, we checked it for small m. Every m that we checked so far is a rational function. And we honestly believe that this is going to be a rational function, and it's a matter of time for us to get there. Okay? Very quickly, if you give me one more minute, I want to give this remark on Shapiro-Chen generalization. So we have seen that all these 4 combinatorial objects enumerated by every other Fibonacci numbers. Okay? Now, Shapiro and Chen looked at these kind of sequences Gn satisfying this kind of recurrence relationship where D is any positive integer. Okay? Mind you, they didn't give any initial condition. You can throw in your own initial condition and come up with your own sequence. You got that? Okay. Now, it's actually not so difficult choosing suitable initial conditions to obtain every other Fibonacci numbers from their generalization in the case when D equals 1. Okay? If D equals 1, you choose suitable initial conditions, and you will see that Gn equals f2n minus 1 satisfies this one for that particular case. Okay? Now, really what they are looking for is for a set of combinatorial objects that are enumerated by their general sequence description for different initial conditions.
I thought D equals 2.
Huh?
I think D equals 2 to get the usual recurrence for Fibonacci even. Fibonacci. Oh, it's
Yeah,
Fibonacci.
this one is odd.
So here I think D should be equal to 2.
For this case,
Yeah, I think so.
I think D is 1. I'll check with you.
Okay.
This one is D equals 1
Okay.
with the initial condition. Maybe when you change the initial, you get even. I don't want to get the even. I want to get the odd Fibonacci. For odd Fibonacci with suitable initial conditions, and D equals 1, I can show you. You can get that. And also don't forget that my initial condition is f0 equals 0 and f1 equals 1. Okay? Now, they are looking for combinatorial interpretations enumerated by these general sequences for different initial conditions. Now, what they did is, since the case of D equals 1, okay, was every other odd Fibonacci, and we know that that enumerates, among other things, skinny trees, they looked at SDN to be the number of skinny trees in which the out degree of each vertex is a multiple of D. Okay? So, for example, when D equals 1, you get the regular skinny trees, the one that we talked about. Okay? So, for example, with D equals 2, an example is this. Okay? So, this is an example of a skinny tree with D equals 2. Okay? At each level, you can have only one vertex that can have children, but the children, the number of children must be a multiple of 2. So that's an example of, okay? And also using this, and then they showed that the generating function for SDN, notice that z to the power of dn here, is given by this rational function, okay? And using some fancy argument about rational functions, it's not difficult from this generating function to show that SDN satisfies this recurrence relationship with this initial condition. That means the general sequence that they introduced, among other things, with these two initial conditions, counts skinny trees in which the out degree of each vertex is a multiple of D. So this is just one example, but you can give your own interpretation for their possible generalization and so on. In our case, we are currently working on a slightly different combinatorial interpretation for the generalization that will also include the standard skinny trees. For that, we are using our previous research on K-trees, which you can find in this paper and so on. I guess at this point, I should give you the list of relevant references on the topic that I talked about. If you want more details, you can get them from any of these papers. And thank you very much for your attention.
And can we begin to answer questions in private? Thank you for the great talk. If you'd like to join us.